So good day. For today we will discuss about angles and directions. So outcomes for this lesson is the student must be able to first identify basic types of meridian. So this is, when we say meridian, this is where we start our uh, or reference line for our angle measurements usually. No? Then second, we will differentiate what is an azimuth and bearing. So what's the difference between the two? And lastly is to convert azimuth to bearing and vice versa. Okay. So usually in angular measurements, the location of points and the orientation of lines frequently depend upon the measurement of angles and directions. No? So before we learn how to measure angles, we learn how to measure distance. No? So when we say distance, um, it is somehow the magnitude in vector terms, no? Vector terms, right? So when you have your distance, no, it's easy to say that we have this length, but how can we say where this line is going to, no? Where it is directed. So it can be represented also by its direction in the form of an angular measurements. So horizontal and vertical angles are fundamental measurements in surveying. So not only in surveying, not we are not only measuring or as we say, we are only dependent to the horizontal, but also we measure vertical angles. So say that you have some features on the ground that we require to measure. Then, for example, that point is somewhere far or somewhere high. Then we have this instrument, what we call the theodolite, no, or transit, which is the instrument used to perform accurate angular measurements in surveying. So we can perform or we can measure horizontal angles or vertical angles. So when we apply a vertical angle, no, so this is where we measure points that above or below the horizontal plane or our line of sight, no. So this is very useful when we measure distances like for instance, you have this instrument, no. So the line of sight is going that way. So you want to measure this point. So you have your vertical angle, no? So if this is your reference, so given that we have this projection of your horizontal line, so this is your horizontal angle, okay? So next we have the polar coordinates and the rectangular coordinates. So we have the polar, no? So which are represented by a distance and an angle from a plane. So you have your d as your distance and theta as your angle. Yeah. So for this one, we can say, let's say x meters. Then this is your angle. Given that your angle, no, when we say angle, it is subtended by two adjacent lines, no. So for example, when we say angle, it must have a central point, no? So this is your pivot, no? So this is your polar coordinates representation. So therefore, let's say this is point P, its coordinates is x and theta. Or in rectangular coordinates, means that they are represented by two distance components, x and y, that are right angles to each other. So we need to say perpendicular. So if we project this one, something like this, no? You project its projection to this plane. So you have your, let's say, east coordinate. Then you project this one to this plane. So you have your northing's coordinate, or east, or with the x, and could be y. Okay. So therefore, point P can also be represented by x and y. No, make uh, x here is the distance component of this line. Okay, uh, we can use also east and north. Okay, so here, mm, so here we can also convert polar coordinates to rectangular coordinates. No, okay. For example, you are given polar coordinates. So polar represented by a distance and angle. So in order for us to convert it into rectangular, so you have x is equals to, so this side, right? X. So you have your angle and you have your distance, no? So this is your distance d. Therefore that is d times the cosine of your angle. Then y it's just equals to d sine of theta. Okay, so that's how you convert. And if you're also given the rectangular coordinates, so let's say x and y, so to polar, so that is, if we want to determine the distance, so it's just simple, square root of x squared plus y squared. Then for angle, that would be arctangent um, y over x. Okay. So since we are talking about angle measurements or angular measurements, so it's important to identify these angles, no? So first we have the degree, which is in sexagesimal system, means that the circumference of the circle is divided into 360 parts or 360 parts, no? So, diba? So 360. So one rotation, so that is equivalent to 360 degrees, no? So this is your symbol for degrees. So this is your symbol for degrees. And 1 degree is equivalent to 60 minutes. And 1 minute is equivalent to 60 seconds. No? Okay. So don't forget about this uh, units. No? Okay. So second, we have the grad, no? Gradients, which is divided into 400 parts or in centesimal system. Then we have the mil, which is divided into 6,400 parts. Okay. And radian is the angle subtended at the center of the circle by an arc length exactly the same to the radius of the circle, in which the circumference of the circle is equal to 2 pi. So, in angular terms, no, 2 pi is equals to 360 degrees. Okay. So, the definition of radians is this one. So, you have your, okay, for example, this is your circle. So, you have your radius. The length of this radius is equals to this circumference. So, this one. So the angle subtended by this one is equivalent to 1 radian. Okay. Then the full rotation of this one is equivalent to 2 pi, or the half rotation is equivalent to pi. So pi is equivalent to 3.1415, etc. and so on. No. never ending and never repeating numbers, no? So anyway, so let's skip about the regens or the pi. Okay, so usually in angular measurements, no, we in order for us to measure an angle need to have two lines, no, two lines. So it must have a common center, such as this one, let's say point O. Then you are observing two points A and B. So given that you are here at point O, you want to determine your, uh, let's say, the angle between these two lines, no? So you have angle distance or line OA, so which means that you are standing at point O and observing point A, and you have line OB, the same, you are standing at point O and observing point B. So the question is, what is the value of this angle? No? So there are so many ways to measure this angle. So today, we have already your smartphone. You can use its compass, no? Or they call it e-compass or electronic compass, no? Another, we have your transit, as mentioned before, or theodolite. You can also use compass, no? The literal compass, no? Device, no? So those are the examples how we can measure this angle, no? Okay. So since we are in the surveying field, there are two types of angles that we are uh, lean to. No? First, we have the horizontal angle, which is the difference between two intersecting lines when they are projected onto a datum plane. So given that you are observing at point A, then you observe 2 points, let's say point B and point C. Keep in mind, they are different in elevation. Mean to say they are not on the same plane, but we can still measure its horizontal distance. So we have what we call the instrument, what we call the transit. No, it's capable of doing that. So from that, in order for us to measure the horizontal distance between these two lines, no, we project them, these points, no, to a common plane. So which we call the horizontal plane. So from this plane, we have your projections of point B, let's say B prime, and we have point C, C prime. No? B prime and C prime are already on the same plane, mean to say they are on the same elevation, then you can measure its horizontal angle. Okay? So easy as that. No? For the vertical angle, so you have this square expressed as your horizontal plane, or we can call this as uh, your horizon. So this is where our uh, level line, no? Or what we call the mm, yeah, the horizontal plane, no? Or the eyesight, no? Okay. So your horizontal plane is perpendicular always to the vertical plane, no? So it's not shown here, but anyways, vertical angle is the angle of elevation or depression between the lines of collimation and the horizontal plane, which passes through the horizontal axis of the theodolite. Okay, so such as this one, we want to measure this point, no? In order for us to measure this point, so we set our instrument, common instrument is the transit. We set our instrument, then once we level the instrument, then we can observe this point. Then from that, we can record its vertical angle. So from there, you have your vertical angle. You can compute its, what you can commonly compute its height, right? Now from the reference line now, or reference eyesight, or the reference horizontal plane, given that this telescope is your starting point. But if you want to purely determine its height, you need to determine also the instrument height, no? In order for this height can be corrected into difference between the the reference point and this point. Okay. So anyways, you just focus what is a vertical angle. So it's a angle of elevation. So when I say elevation, this is your horizontal projection, it's going up. For depression, your vertical angle is going down. Okay. So for this one, so you can see the combination of the horizontal and vertical angle. So from this one, you can see that this is your horizontal and this is your vertical angle. Okay. So now let's proceed to the meridian. Okay. So a meridian is a real or an imaginary reference line of fixed direction. So the direction of a line is defined by the horizontal angle between the line and an arbitrary chosen reference line called a meridian. Okay. So the following, we have five, are the usual meridians used in surveying. Okay. So when we say meridian again, no, this is what we call, or where we refer our angular measurements. So reference, this is where we start, no? So what is a common meridian, diba? You have your north direction, right? Or when you are using your smartphone, you you turn on the app which is called compass, then it will point you, or it will somehow tell you where is the north. So that is your meridian. Okay. However, meridians are divided, or uh, expressed in different ways, no, or referred to different meridians. So though meridian in general, this is where we refer our angular measurements, no. This is where we start, or the starting line, no. However, meridians are referred to different setups or definition. First, we have the true meridian. So true, or sometimes we call it the geodetic meridian, which a line passes through the north-south poles or the geographical poles of the Earth. So I'll show you an example of geodetic. So usually it determines the mean pole, no? Okay, because the polar movement varies time to time, no? So thus there's no constant, or it's temporally it's temporally dependent, no? Okay. Next, we have the astronomic meridian, which is the north-south reference line that passes through the instantaneous position of the Earth's geographic poles. So somehow, 1 and 2 are quite the same. And if you determine the true meridian, you only required a small amount of correction to determine the astronomical meridian. No, sometimes this is quite obvious that they are not the same, but most of the time they are just almost equal. Next, we have the grid meridian that is parallel to the central meridian. Okay, this is used when computing points in planar rectangular coordinate systems of limited extent. Imagine that the Earth is not plane, so therefore, when we use a grid meridian, this is not advisable when we are covering large tract of land. However, if your area is limited, then we can use the grid meridian system. So maybe I'll show you later the image, the difference between the three. Next, we have the magnetic meridian, which is it lies parallel with the magnetic lines of force of the Earth. Its direction is not constant because the magnetic pulse is constantly changing. So from time to time, by definition, your let's say you are at this place. During 2000, year 2000, this is the magnetic north. During 2010, the magnetic north changes. No? So that's how varying the magnetic north of your magnetic meridian changes. No? Then next we have the assumed meridian. When we say assume, so it's an arbitrary or chosen meridian, meaning to say you are just assuming this is the north for maybe for you to start your survey in case you don't have a compass or any device that can determine the correct meridian, such as the first four, right? Okay. So here, this is an example of a meridian. So this dark black line, this is what we call your meridian. So it could be your true meridian. No? And this red line is what we call the parallels. Okay. So usually in grid, this represents in terms of global positioning, it's easy to locate points by geographic position. You have your latitude and longitude. No? Okay. So for the meridians, it's very important to also to know where is your meridian, because from this you can measure, or you can actually measure the angles if you are oriented. No, if you're not oriented, then you can choose and assume the region. No, okay. So here, as discussed lately, no, the difference between the astronomic meridian and the geodetic meridian is this. No, when we say astronomic, it's the instantaneous polar position during that time. Where is the pole? No, we all knew that this is the pole, um, but in reality, the your polar or your pole is actually moving, such as in this figure. No, so during the 1900s, the pole is right here. So this is the somehow what we call the north pole, no, but the polar axis, due to the uh, different different factors such as gravity, the landmass of Earth, the perturbations of other planets with respect to the gravitational properties of the Earth, no, your pole changes or moving, no? So moving, it's always moving. So that's why the 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 difference between the two is the true pole, or not the true pole, but the true meridian always refers to your mean pole, but the astronomic meridian always refers to the instantaneous polar position. No? Okay, so that one. But this difference is just quite small, no? So probably less than 1 arc of a second. So that quite small, no? Okay. So here shows the grid. So when I say grid, such as this one, no? So when I say grid, this one, okay. So for example, the difference between the two meridian, the grid meridian is always, or it's somehow straight, no? From the previous images, the meridian is somehow like this in curvature, no? Meeting at a common point, which is what we call the pole. But for the grid meridian system, no, they doesn't meet at a common point, no. But however, portions below the equator and above the equator seems to be distorted in terms of area and its representation. However, Philippines somehow is near the equator, then we have uh, slight changes in terms of the representation in the area. So this field covers, or it is already covered by map projection field. So we will not tackle more about that. Okay. So how do we establish meridians? Okay. First, can establish a meridian by a magnetic compass or by compass. No. So when you use compass, it is purely influenced by your magnetic pole, thus pointing you the magnetic north. Okay. Then how do we also determine true north and or the true north or the true meridian? So it is by observing Polaris. So Polaris is the what we call the North Star, no? Or sun. So we can use those heavenly bodies to determine the true direction or the uh, true orientation, no? Or to determine your meridian. Remember, magnetic meridian and true meridian, or as well as the astronomic meridian, uh, varies, no? So when I say true, that's the true direction. But sometimes, from the true direction, your magnetic meridian deflects. Sometimes on the eastern side, and sometimes your magnetic direction deviates also along or to the west. No, because it is affected by or influenced by gravity. So gravity changes over time. So thus the direction of your magnetic compass or magnetic north changes over time, but not so with the true meridian, because your true meridian relies on heavenly bodies, and that's it. No, it has slight changes or no changes at all. Then the third one, we have the GNSS techniques. So when I say GNSS, it's Global Navigation Satellite System, or the common term, we have the GPS, Global Positioning System. So by that, we can also employ this technology to establish a meridian. No? Okay? So somehow this is advanced for this topic. So at least we can recognize that we can also use a GPS system for or the GNSS uh, methods in establishing meridians. No? Remember, if you have your smartphone, it is already equipped with satellite positioning mechanism. So therefore, um, you can already establish a meridian, but not that precise. No? So in terms of preciseness of a meridian, it's very important to perform it using uh, an instrument that are capable of producing a precise measurement, such as transit, theodolite, and as well as the survey grade receivers of GNSS. Okay, so directions of lines, no, right? So the direction of line is defined as the horizontal angle of the line, which makes with an established line of reference. Okay. So usually when we talk about line, we have this question where this line pointing at, no? So if you have only a single line, you will have guessed, I don't know where this is pointing at. But if we add a reference meridian or reference line, let's say your true north, then we can define this line, no? We can define that this line is pointing at 30 degrees from north, no? So 30 degrees from north. Okay, so we can already define this line, but without this reference line, you cannot define or you don't know where that point or where that line pointing at, right? Okay, so in surveying, in terms of horizontal angle, directions may be defined by means of the following. So first, we have your interior angle, deflection angles, angles to the right or left, no? So right, so it's just telling us the direction of the rotation, right? Then we have bearing and azimuth. Or so I highlighted the two words here, the bearing and the azimuth, because this is what we are focusing into. Huh? So when we say interior angle, it's the angle between adjacent lines in a closed polygon. So such for this one, this is your interior angle, no? It could be the direction of measurement is going that way or that way. It doesn't matter as long as you have a reading of this one. So let's say this is 60 degrees. So angle ADC means say you started at A, this is your center, and this is your going to is 60 degrees. No matter what's the direction of your measurement. Then we have the sum of your interior angles. Mean to say, what's the sum of your interior angles? It's basically using this formula. N is the number of sides. Okay. Then you multiply it by 180, then that's your summation of the interior angles of that specific polygon. Okay, so for a triangle, you have three sides. So that's why the summation of the interior angles of a triangle is 180. 3 minus 2 is equals to 1 times 180, then 180. Okay? Then next, we have the deflection angle. So, it's the angle between a line and the prolongation of the preceding line. So here, if the survey progression is on this direction, I mean going that way, no? So you started at point A, then B. So AB here is the preceding line. Then at B, we have the extension, or we have the prolongation of the previous line or preceding line, which is line AB. No? Then we have line BC. So therefore, the deflection angle for line BC using line AB is this one. So this is your deflection angle. Okay. So for this one, since this is your reference line, so this is an angle to the right. So angle to the right, or using symbol positive. Then let's say going to point D. So angle of line CD, we have this deflection angle left, or angle to the left, represented by a negative sign. So for example, this is 40 degrees, and this is 50 degrees. So therefore, the deflection angle of line BC is equals to plus 40 degrees, or 40R. Then we have angle CD. We can say that that is negative 50 degrees, or 50L. So that's how you read or write a deflection angle. So just look at the figure, no? To define this specific line, all you need to have is to project the preceding line, then measure its angle. Okay, so it could be to the right or to the left. Okay, then we have also angles to the right. No, angles to the right are measured clockwise from the rear to the forward station. So when we say rear, the previous station, then the forward is the next station. Okay, so angles to the left are turned counterclockwise from the rear station. Okay, so take note, as the survey progresses, stations are commonly identified by consecutive alphabetical letters, or in alphabetical order. So usually in surveying, we have point A, this is where we start our observation, then we go to point B. So we observe the previous station or rear station, then we start our measurement here, we set the angle reading 0 here, then we turn the measurement, or we measure its angle going to the right. Then for this one, then this is the representation of angle to the right reading. No? Okay, so that way. So for this one, so we have also angles to the left. Angles to the left or to the right, it's just the same. The only difference is where's the angle of rotation turning into. No, it could be to the right or to the left, or clockwise or counterclockwise. No, at a given station, let's say point A. So you read to a rear station, let's say point F, then you have your forward station point B, then you have your angle to the right. Then at point B, your rear station is now point A, then your forward station is point C. Then you start your measurement with this line BA, then you end your measurement at line BC. So this is the projection of this line. Okay, at point C, the same, your rear station is B, and your forward station is D, then that's your interior angle, or angle to the right. For this one, the direction is different. opposite one. You observe you are at point A, then you observe point D as your rear station, and you have your angle there. So you have your point B as your forward station. So this is an example of uh, an angle to the left. Okay. Now let's proceed to the most or the important angular measurements in surveying. So we have the bearing. So bearing is an acute angle between the reference meridian and the line. So this bearing or this angle may be referred to a true meridian, magnetic meridian, grid meridian, or assumed meridian. So any of those, as long as the meridians uh, are defined well. So the bearing of a line is indicated by the quadrant in which the line falls and the acute angle which the line makes with the meridian in that quadrant. So here, bearing always refers to your reference meridian. Say the north-south line, no? So again, by definition, it could be referred to a true meridian, magnetic meridian, grid, or assumed, no? For this case, let's just assume that your north-south line always refer to a true meridian. Okay? So for this one, your bearing is an acute angle, always an acute angle. So starting from the north-south meridian. So it could be at point A, your bearing, we have only one possible bearing for this one, starting from the north line going to this line, no? Your bearing cannot be in this direction, okay? Because it is always an acute angle, okay? For point B, your bearing cannot be always from the north, no? So it's not that way. So your bearing must be an acute angle, so it can start from the south line instead. Then that's your bearing of point B. Then for point C, again, cannot start from the north or north, no? Then it cannot also be this way, no? So not that direction. So but instead, starting from the south line, going to the line OC. Okay? So remember, your bearing is always an acute angle. So find a way to measure your bearing of a line, no? So where do we start our measurement? So it's always from the north-south meridian or line. So that's your reference meridian for your bearing measurements. Always acute angle. Then for point D, so by this angle, okay? So what happens when the line falls along the quadrant? Then for example, okay, before we proceed on that, there's a naming convention for bearings, no? Okay, so let's say OC, oh no. First we will proceed with OA. So what's the bearing of line OA? So it could be, or this is how we name a specific bearing. So when we say bearing, we always name in this way, okay? Okay, bearing is equals to N or S, mean to say where it started, from north line or south line, then the angle, then east or west, mean to say where it points to, going to the east or going to the west. Okay, so bearing of bearing of line OA. So we all know that this is 70 degrees. So 70 degrees. So the question is where it started from. So remember, it could be north or south. It is always starting from north or south. So therefore, coming from the north line. So north, 70 degrees, where it pointed to or turns to, going to the east or west. So it's going to the east. So therefore, north 70 degrees east. Okay. Okay. Another one. Bearing for line OP. So it could be north or south. It's south. South. Then the angle 35 degrees east or west. So east. So therefore, the name of this angle is of line OB is south 35 degrees east. South 35 degrees east. How about line OC? So that is south 55 degrees east or west. So it's west. Then bearing of line OD is north or south. It is north 30 degrees east or west. So west. Okay? So that's how you name an angle. Okay? So let's talk about the forward and back bearing. So when the bearing of a line is observed in the direction in which the survey progresses, meaning to say this is where our direction or the survey progression, no, going in that direction, let's say from A to point B, so that's your progression, then it referred to as the forward bearing or bearing. If the bearing of the same line is observed in an opposite direction, it is referred to as the back bearing. So given that this meridian are specified into specific meridian, let's say true meridian, so this is your true north. So therefore, for this figure, line AB, so this is your, given that this is the progression of the survey, so this is where you're leading to. So this is your, what we call the forward bearing. Then at point B, this angle is just equivalent to your forward bearing, or therefore this is what we call the back bearing. So meaning to say, these angles are equal, or what we call opposite angles are equal, no, in geometry or in geometry theorem, right? Therefore, the only difference is if your forward bearing, let's say forward bearing of line AB is, for this example, okay, say theta. So this is south theta east. So the back bearing of line AB is just simply north theta west, no, opposite direction, opposite in direction. Okay, so here, so that is north then west, no, so that's, but the angle, the value of the angle are just equal, no, only the direction changes from south to north, then east to west, or if this is north, this would be south, and if this is west, this could be east. The only technique for you to understand is to draw the angle and able to observe which this angle directs to. So next we have the azimuth. So the azimuth is the angle between the reference meridian and the line measured in clockwise direction. from either north or south branch of the meridian. So the values are ranging from 0 to 360 degrees, and with letters such as northeast, northwest, southeast, and southwest, no, are not required to identify quadrants, no. Okay, so for the bearing, if the angle is north 90 degrees east, that would be equivalent to due east, no. So for you to understand this one, this bearing, try to draw this bearing. But for the azimuth, usually in the Philippines, no, Philippines, double P, usually the reference meridian always from the south branch. So meaning to say, the angle measurement starts here, going to this direction, no? But for this example, the reference meridian started at the north branch, going here, no? So anyway, let's erase this first. Okay. So azimuth is the angle between the reference meridian. Reference meridian, it could be north branch or south branch, and always in clockwise direction. Then values ranging from 0 to 360. If the azimuth is 360, therefore it's just equals to 0, right? So that's your azimuth, no? So for example, azimuth for point or line OA. So if it's your reference meridian is from the north branch, then this is the angle. But if it is defined that your azimuth must be referred from the south branch, then this is now your azimuth of line OA. So usually in the Philippines, we all refer our azimuth on the south branch. Okay. Okay, so for point or line OB, so for the south branch representation, this is your azimuth of line OB. Okay. Okay, for this one, if given that the reference line, the reference meridian is the south branch, so what is the azimuth of line OA? So if from south, so that would be 180 plus 70, so that would be 250 degrees, no? So this is 180, let's use another color. This is 180, then you add 70, then that's equivalent to 250 degrees. So in azimuth, there's no need to put N or S or E or W compared to bearing, right? It's just simply the value of the angle. But we make sure, we make also pre-identified that this azimuth is from the south branch or north branch. But to be safe, in the Philippines, we are using the south branch instead of north branch. Also, this was also used in the military, no? They prefer the south branch rather than the north branch. Okay. Then we have the conversion for forward and back azimuth. So these are the following rules in getting the value of back azimuth when forward azimuth is given. Okay. So if the forward azimuth is greater than 180, then we subtract 180 degrees to obtain the back azimuth. Okay, for this one. Given that your your line, let's say line AB, this one, then this is your south, then north, west, east. Given that this line, this is your forward bearing or bearing. Therefore, this is greater than 180 to get this. So this is also your back bearing. Okay. Let me. Okay, I will draw this clearly. So for example, you have that one. Okay. So you have this. Okay. So say this is point A, this is point B. Therefore, this is your forward azimuth. Okay. So this is your forward azimuth. So greater than 180. So this is also your back azimuth. So to determine your back azimuth in this figure, just simply the forward azimuth minus 180 degrees. So if you deduct this angle into deduct this whole angle by 180 degrees, so the angle left is this one. So this angle, let's say angle phi, is just equals to this angle. So that's why we have this equation. And for the other case, if the forward azimuth is less than 180 degrees, then we add 180 degrees to determine its back azimuth. Okay? So let's have a comparison between the two. So in terms of angle and size between bearing and azimuth, bearing is always an acute angle, no? Ranging from 0 to 90 degrees. Then for the azimuth, from 0 to 360 degrees. In terms of direction, the azimuth is always in clockwise direction, so always in this direction of rotation. For the bearing, so it could be this direction or this direction, depending on where the line lies, which quadrant, right? Or if your line is within this zone, then its direction is going that way, right? Or if your line is about here, then its direction is going that way, right? Okay. So hopefully um, it's been clarified the difference between the two angles. Okay. So assuming that the azimuth are from the south branch, so these are this is the yes. So this is how we determine its bearing, right? Okay. So kindly remember. So if your azimuth is within this quadrant, that is equivalent already to your bearing. So you can say that the bearing is equals to the south uh, equals to south, then the value of your azimuth west. For this one, your bearing now is north, then 180 degrees minus the azimuth, then west. Then here, your bearing is north, then the azimuth minus 180 degrees east. Take note the equation, right? Then here, the bearing is south, then 360 degrees minus your azimuth east. So that's how we convert, no? Then if you want to determine the azimuth of that line, given that you have your bearing, so you just simply configure the formula, no? So one thing for sure is you need to draw the figure in order for you to identify, this line falls in this quadrant, so I will use this formula. This line falls in this quadrant, so I will use this formula in converting azimuth to bearing or bearing to azimuth, no? So do not rely on your imagination, but you need to draw in order for you to identify, okay, this line falls in this quadrant. Okay, so before we proceed to the example, so we have reference direction for vertical angles. So this is what we call your horizontal plane. If you have a point here, so you have this is your example of a vertical angle, no, or angle of elevation. Then if your point is somewhere lies here, then you observe your angle downward, so that is your angle of deflection, no? So therefore, in this figure, you have your zenith angle, which is complementary to your vertical angle. So therefore, in this figure, zenith angle plus the plus vertical angle, that is equals to 90 degrees. Okay. Then we have also your nadir, which is opposite in direction with the zenith. So when you say nadir, that is pointing downward. Okay. So now let's go to converting azimuth into bearing, given that these azimuths are from south branch. Okay, so for example, we have 225 or 225 degrees. Okay, let's draw a figure. So from south, 225. So this is 180. This is 180. Then somewhere here. So this is the line. Okay. So therefore, this is north, east, south, and west. So therefore, in order for us to so this is 225 degrees. In order for us to identify the bearing of this line, so therefore, bearing is equals to what? The given azimuth. Azimuth minus 180 degrees, so that we can what's left is this angle, no? Okay, so therefore if we continue, that will be 225 degrees minus 180 degrees, then that would be how much? So 180, that would be 45, right? So 45 plus 45, yeah, that would be 45 degrees. But since it's a bearing, so that would be north, then going that direction, so east, north, 45 degrees east. So that's your bearing for that example. Okay, so here I'll add some bearing to azimuth for you to practice. Say north 35 degrees west. Then the other one is south 50 degrees west. And the last one is south 30 degrees east. Okay, so I'll give you one example. How do we convert this okay, this bearing to azimuth? Okay, given south 30 degrees east. Remember, you always draw a figure, then identify north, east, west, south. Identify where this angle falls or line falls. So therefore, na south 30 degrees east. So going to the east. So therefore, somewhere here. So this is your 30 degrees. So in order for us to identify its azimuth, so its azimuth is in clockwise direction. Then starting from south because we're in the Philippines. Then going that way. So therefore, azimuth of that line is just equals to 360 degrees minus the value of your bearing, which is this one. So 360 degrees minus 30 degrees, that would be equals to 330 degrees. So that's your bearing of that line, or the equivalent bearing. I mean, the equivalent azimuth of the bearing given. Okay? So, this ends our lesson, and I hope you get something from this lecture. See you in our next lesson.